So effort source for this kind of source where you have a voltage source, flow source or velocity source when you have the change in the vertical position as a function of time, such as in the case of the suspension. The representation of those two is done by the symbol. So you see, here's the SE, and you say what is out of the SE is this effort in here. So the system in this side, there will be the system on this side responds with the flow, see? Now, in the case of the flow source, we have the reverse situation. So let's see if we can do just some annotations in here. In here, for example, this is the source. So this is the source, yeah? Source. I don't have my tablet today, so it's a little hard, but in any case, what goes out of the SF towards the system is the flow, this variable, this one. And here's your system. From the system into, feedback is this effort, see? So that's why you see that the causal mark is going away from the source of effort, but it's the other way when it's in the source of flow. So that's important to keep in mind. So let's go down here. If we represent this source effort as a block diagram, this is what you would get. Or if you represent it as a bone graft model, this is what you'll get. So I want to make sure that by the end of this class, that you have a vision on how to do models of systems using either the block diagram method or the bone graft method. There are two ways of representing systems. This is the block diagram that represents the source of effort. This is the block diagram for the source of flow. But always a two-way street, see? Effort this way, flow this way. That's what this means. And in this case, effort this way, flow this way. So I think just to make sure that we can make some notes here, just if this is helpful. See here, this is the effort here on this side. This is the flow, like that. Same thing here, this is the flow. And in here, this is the effort. So it is important to make sure that we understand how that symbol works. Okay. Let's go on. Now we have to look at these elements. These are what we call two-port elements, because now this transformer element, or TF, is an element that conserves energy, but only transforms either a flow into another flow or effort into another effort. But of course it has a transformer modulus, meaning some constant that allows the transformation to happen. A best example of this would be a set of gears. And of course this one too is a transformer, because it transforms the force here into a pressure here, and transforms the velocity here into volume flow rate. So whenever there is that relationship between the effort and the effort, the flow and the flow, you have this element called the TF. So in here, if you have lever, for example, isn't it true that you could establish that the velocity of this point is omega times a, and the velocity of this is omega times b? If you equate those two, you get this expression right there, this one. But that same is true for the forces, see? So A over B becomes the so-called transformer modulus. And in this case, that transformer modulus that relates the force to the pressure is the ratio of the two areas. Same thing here. The one that relates the velocity to the volume flow rate is the ratio of the two areas. So this is a transformer is a power conserving element that transforms effort into effort or flow into flow. The representation in the bond graph way, you have it in front of you in there. And in this case, you need to read it in such a way that you read it both ways. You read it this way and you read it this way. Let me explain you what that means, so that let me just perhaps so that everybody can see it up closely here. You see in here the green line that you see here is the input to this TF. And the green line that you see on the right hand side is the output to the TF. That is looking at this matter this way. Now we are going to look at this way. Remember the two-way street? That holds true here too. The flow goes this way, the effort goes this way. How in the world is that represented? You see in here this E, this E2 is the input to the TF, and the output this way is this effort E1. And if you go this way, the flow is the input to a TF, flow 1, and F2 is flow, the output. Now, because there's always these two variables, remember this so-called power transformation variables. If you have the input like E sub 2 multiplied by M, you're going to get E1. And that's what this equation reveals, the one at the top, this one. Or if you have F1 multiplied by M, you get F2, see? So the transformer always has two equations. You know the unique things that we have, like in the resistive element, you have voltage equals I times R. It's easy to remember. On the C element, you have Hooke's law, K equals to K, F equals to Kx. And in the inertia element, Newton's law that says F equals to mass times acceleration. On this one, you have to remember that one flow or velocity gets transformed into another velocity by this modulus m. So we have to remember always that the TF has two equations, not one, two. But you can have it like this, or you can have it this way. So how does this work? You see on the right hand side, you have E1 over here multiplied by this M prime, you get E2 going this way. So E1 times M prime equals E2. You see the equation in there? Now, so we went this way, right? Now going this way, F2 is the input to TF, multiplied by M prime, it goes to F1, and that's this one. See? I think instead of memorizing this, I think that's the best way to learn this transformer element. Is looking as to what is the input and output in this side, what's the input and output on this side. Let me see if you guys are following me. Take a look at this side. what is the output here? No, here on this side, on the left. What is the variable that is the output? It's E1 because it's going away from TF and the input is F1. And on this right hand side, what's the output? F2. And what's coming in is E2. That's how you read it. Okay? This thing would never happen. This is totally not possible. The one on the, or this on the bottom. I just told you so that you realize this clearly. Now here you have the TF element that you see you have E5 times the module, you get E4, or F sub 4 times the module, you get F5. See, this thing in here, reading it this way, you get this block. Reading it this way, you get this. Remember what I said, always two equations. So let me see if we could make some notes and be able to write this hopefully in a good way. So here we go. If you go to the top, you say the input on the left hand side is E sub 4, right? Times the module of the transformer should be equal to what? F5, okay, hold on for a second. I think we have a little mistake in here. Let me start over again. Okay, what's the input on this side? Is F sub 4, right? So F sub 4 times the modulus M should be the output, which is what? This one, F5. So this is going this way. Going this way, we have the input would be E sub 5. So that would be E sub 5. This multiplied by M should be equal to this side in here, which is F sub 4, right? This is on the left hand side is, no, excuse me, this is E sub 4. On this one, let's practice this one so that you get some practice doing this. What is the input on this side? Here is F sub 4 times the TF is F5. Okay, so these are the two equations that we have for this. Okay, now if you have it this way, you have E sub 4 times the modulus E5, so that's what this is, or that F5 times M is F4, that's what this is. So you can write the equations in both ways, and you can see the representation here in block diagram as well. Any questions about what I just said? No? Okay, now we go to this gyrator element. This is also a two-port element that we need to deal with. The best example of a gyrator element is a DC motor. A motor that you see it on the right-hand side over here. Here's the motor. As you can see, the voltage to the armature is here, and based on that voltage, the motor produces a torque, an angular velocity. There's a relationship between the voltage and the angular velocity. You may recall when you were a little kid, if you had one of those toys like a train, for example, you had a dial, and if you move the dial, puts more voltage to it, and then the train goes faster or slower. That's the typical case how a DC motor works, because that is used in all kinds of applications, including the one I just mentioned. You can have a gyrator like a gyroscope, which is on a mechanical system, which you see in there, and that has a relationship between a velocity and a torque. Okay, for this case, like F1 is the modulus of this gyrator times V2, or that R times V1 is F2. When you have this kind of relationship, you need to realize that we have a situation where, let's just make some notes in here. You have a situation in here where you see that E, this is the effort variable on this side, yeah? But you see this is a flow variable here. I'm just going to make an emphasis. This is E, this is the flow variable, related by a module. So these two are not the same kind. That's what the difference is between the transformer and the gyrator, because the transformer goes E to E, but this goes E to F. And the other way, see here, this is a effort variable, here this T, we could just write it down here, effort variable. This is the result of a flow variable, which is I here, multiplied by the gyrator modules. So this you have F, see if we can write down well, F equals R time, F times R equals to T. Or you could say F times R in here equals E. See? So the gyrator is not a transformer, it's very different. So now, if you look in the bond graph representation, you have two cases. You have this one, and you have this one. You have in this case, let's take a look here. What's the input to the gyrator on this side? The input is F1 times R is E2. See, that's what this equation says. The input on this side is F2 times R equals E1. And that's what this equation is. Let's practice over here. This is also possible, this causality here. The input on the left, this is E1 times R prime is F2, and this is E2 times R prime is F1. You see what I mean? It goes always this way, but also this way. Same thing, this way, this way. Is there any question about how this representation, about this representation of the equations? One thing I want to say to make sure that I emphasize that is that the gyrator causal marks, as you can see, the two on the two red ones on the left as outputs, and you have two of the green ones on the right as outputs as well. But the green ones are flow, the red are effort. Depending on how it's connected, it will acquire one or the other causal marks. So that's what I can tell you about this element, so-called gyrator. If you look at in the block diagram way, the fact that an effort relates to a flow, or that this effort relates to this other flow in the other way, makes it that the signals cross like this. So in fact, in many books you will find that the gyrator is called a cross transformer. In other words, those two elements are cousins of each other. And either this way, like this, or this way. Yeah? So this F1 times the modulus is E sub 4, or this would be F sub 4 times the modulus equals E sub 5. So that's what that is. Okay. Let's see.